Hello everyone! In the previous video, we created a simulation of an electrical discharge using a line with multiple segments. This time, we'll stick with a similar concept, although we'll approach it a bit differently. We'll create something like an ECG monitor that displays the characteristic heartbeat waveform. So, let's get started. So, as usual, I'll open the Godot editor, which at the time of recording this video is version 4.7.1, and create a new scene with the appropriate node and shader. So right-clicking the scenes folder, create new scene is going to be user interface type, and I'll call it heart monitor. Okay. So I right-click the root node, add child node, which is correct, and in the inspector I'll change the color to black, change the layout to the full HD resolution, so it will be the size property 1920 by 1080, okay, and scrolling down to the material section, where I create a new shader material, click it and create a new shader, which is type shader mode canvas item, the name heartmonitor.gd shader, and I'll put it to the shaders folder, create, and clicking again to open it in the shader editor. And as almost always, I'll delete everything from the generated code that we won't need, leaving only the fragment function, deleting vertex, and deleting the commented out light, Ctrl S to save. Okay, so we'll start with the uniform parameters. The first one will define the dimensions of our effect so that we can correctly calculate the aspect ratio. So let's put it here, uniform vec2 resolution equals vec2 1920 and 1080, which is our full HD resolution as the default value. Our effect is animated, so we need to control its animation speed. That will be our second parameter, uniform float speed with a hint range, and the initial speed I'll set to 1, and the range will go from 0 to, let's say, 10 with the step point 01. Okay, next we need two colors, one for the main effect and another one for the background grid. So uniform vec3 RGB colors, line color with a hint source color, which adds this nice color picker into the inspector, and the initial color vec3.1, 1, and 0.1, which will result in a shade of green. Alright, and similarly the grid color, uniform vec3 grid color with a hint source color, and this time I'll set it to 0.01, 0.05, and 0.01. So it will be a very dark shade of green, but then we'll fix it by changing the gamma correction. Okay, so we'll also want a way to shape the appearance of the final graph. For now, it's enough to add parameters to adjust the line thickness and edge blur. Uniform float line thickness and hint range, and the initial thickness 0.01, and the range goes from 0 to 1 with the step point 01, and a uniform float line blur with another hint range, and this time the initial blur equals 0. Okay, nothing is blurred initially, and it goes from 0 to 1 with the step point 01. Finally, I decided to add a parameter that controls the blur of the bright dot, marking the current starting point of the graph. Okay, let's add it here. Uniform float dot blur with the hint range, and the initial dot blur would be 1, and again it goes from 0 to 10 with the step 0.01. Alright, so with the parameters out of the way, we can move on to writing a few helper functions. This is also a great opportunity to reuse something we've already created before. You may remember this shader, which was also one of the first ones featured on this channel. I'll simply take its drawGrid function and copy it into our new shader. Okay, so let's expand this window a little bit, and right after, before the fragment function, I am pasting the function drawGrid. Notice that I've hard-coded the grid line thickness, which is in this smoothTap function. I could expose it as another parameter, but since it's just the background, that would probably be unnecessary. Okay, if you want to understand how this function works, I definitely recommend to watch the mentioned tutorials, and I will link it in the video description. Okay, so now let's move on to the fragment function, where we'll render the grid. And as usual, I'll insert the code to shift the origin, to coordinate origin, recalculate the aspect ratio, and set up the time variable. This time, I'll store the aspect ratio into a separate variable, because we'll need to use it in several places. So let's do it. First, coordinates origin, so vec2 uv equals uv minus 0.5. Now it's in the center of our color act. Then the aspect ratio float aspect equals resolution x divided by resolution y. And then we need to recalculate the aspect ratio the usual way. Sorry, uv.x is multiplied by the aspect. Okay, aspect, no aspect y. All right, and finally the time variable float time equals time internal time times our speed parameter. Okay, and now drawing the grid. So vec3 color equals our function drawGrid with the parameter uv times 10, which is simply a zoom factor. So we have a grid with a square of size, so we need 2, and this is just a float value, so now we need to multiply that by our grid color. And finally, let's put it to the output, which is the color variable in capital letters, and it is a vector 4 consisting of our color and 1 for the alpha channel. Okay, so right now we don't see anything, but because the reason is that I chose a very dark shade of green. However, as soon as I apply gamma correction to the color, everything becomes visible. So let's insert it right before the color definition. Color equals power of color to the power of vec3 1 divided by 2.2. Okay, and yeah, now we have it. So why am I using gamma correction this time? I found that the final effect simply looks better this way because we'll be working with various highlights and emphasizing different parts of the shader. Since gamma correction adjusts what we perceive as luminance, the final result is much more pleasing to the human eye. So let's continue. As I mentioned, we'll add a few helper functions that will be very useful for drawing the animated line. As we already learned in the previous tutorial, where I simulated an electrical discharge, we'll once again need the distance from the current pixel to a line segment, that is, a line defined by 2 points. The formula for the calculation looks like this. And I'll add it as another helper function. Let's expand this window and add it right after the drawGrid function. Float segment dist for distance and with parameters vec2 b, vec2 b, our current point, vec2 a and vec2 b, the 2 points that define the line segment, and the formula, which I already used in previous and many other tutorials, looks like this. Return distance b, and let's clamp it to the range from 0 to 1, dot product of p minus a and b minus a, and it is divided by another dot product, and this time b minus a and b minus a. So it is a projection, and the clamp range is, as I said, 0 and 1. All right, and let's multiply the result by b minus a plus a. Okay, and this should be correct, I hope. Yeah, I suppose it is. All right, we'll also need a smooth fall-off function to separate different parts of the effect without creating harsh edges. Once again, the exp function with a negative parameter is a great choice for this. I'll call this method fall-off, and it will look like this. Let's put it right after this one. Float fall-off with the parameter float x, and it's simply return exp of, I could use negative x, but I think I got a better result with the x to the power of 2, or x by x. So it's negative power of x to the power of 2. All right. For the remaining code, we first need to decide what shape the final light should have. Let me compare this with the previous tutorial again. There, we divided the line into equal intervals along the x-axis and assigned the random positions to the individual vertices. This time, we'll take a more deterministic approach by defining an array of vectors with the exact coordinates of each point. The code I prepared contains a total of 13 points and looks like this. Okay, and since it's a constant, let's paste it right after the uniform parameters, and here it is. Const vec2 points 13 with this array. If you'd like to use the same values, now it's a good time to pause the video and copy them from the screen. Another and probably easier option is to use the finished shader included in the Godot shader pack, which is linked in the video description. Of course, you're also welcome to use your own array of values. The important thing is simply to keep them within roughly the same range. Okay, so now we can write a function that calculates the distance to the nearest segment of our final line. We'll simply iterate through the points array I just added and compare the results. So let's scroll down, and right after the fall function, I'm adding a new one, which will be called float closest segment with the parameter vec2 uv, our current pixel, and simply let's start with min dist float. Min dist is some big value, so let's say 1e9, which is 1 billion. And now we will do the comparison. So float for int I from 1 and I less than points length in the I++, and inside the cycle is the comparison. So min dist equals minimum of our current min dist and the result of the segment dist function with the parameters uv and now points with the index I minus 1, and the second point is points with the index I. Okay, so the from and 2 points. This is why we have this loop from 1 and not from 0, because we need I minus 1 index as the start point. Okay, and finally we will return the result, return min_dist. All right. We will use this function immediately in the fragment function, so where I'll store its result into a new variable. So let's add it right after the definition of vec3 color float min. This is simply the result of closest segment with the parameter uv. Okay, next, to ensure consistent results across different resolutions, we will use the resolution of our color rect as one of the parameters when calculating the line thickness. So, float, let's call it pixel size, and it will be 2 divided by resolution dot y. Okay, y2. If I use the 1 here, the result would look too pixelated. Using 2 gives us a much smoother appearance. For the next few lines of code, we'll also need a macro, which I'll place at the beginning of the shader. So I'm scrolling up, and right after a shader type canvas item, let's add it hash define, and let's call it s with the parameters edge 0, edge 1, and the value. So this is, as you might already know, the parameters of the smooth step function. And the actual formula is 1 minus smooth step. I think there is no code completion in this part, so let's just write everything by hand. Edge 0, edge 1, and value. Okay, so what's the purpose of this macro? If we used a regular smooth step to calculate the line segment, the result would be inverted in this case, that is, black on a green background. That's because we'll be blending it with brightness variations to create the illusion that the graph is moving. So we need to subtract the result from 1, giving us the opposite, a green line on a black background. And since that explanation probably wasn't very clear, it's best if we just continue writing the code and watch the effect gradually taking shape. So I'm scrolling down back to the fragment function, and here I'll use this macro and store its result in a variable called line. So right after the pixel size, let's continue. Float line equals s, our macro, with the parameters line thickness, okay, then line blur plus pixel size plus line thickness. Okay, and the last parameter is our min_dist value. Okay, and something is not correct. Line thickness, it is the correct, I had 3 S's here, sorry. Now it should be fine. Okay. We can now display the result by blending the color variable, this one, which already contains the background grid with the color specified by the line color parameter. So let's do it right here. And since we'll finally get some other result, let's show the 2D editor. So right after this last line, defining the line variable, let's do this color equals the mix of color, line color, and the white value is line. Wait for it. Okay, that's not bad. It's obviously not the finished effect yet, and we'll need a few more refinements, but we can already test how the line thickness and line blur parameters behave. So let's go to the inspector and expand shader parameters. And here, for instance, if I change line thickness, it's definitely thicker, or putting to 0, it has its minimum thickness and line blur. That's exactly what we would expect from it. Okay, perfect. Of course, if we wanted finer control over these parameters, we could adjust the hint range values or simply divide the result by 10 or 100. We can also verify that changing the values in the points array changes the shape of the line. So let's scroll up to our constant point 13 and let's, for example, find this biggest I would say spike, and it should be probably this 1.5. So if I change it to negative 0.3, now it's lower. Let's get back. Or we can change its x coordinate. Now it's 0. Let's change it to negative 0.02. It should be moved a little bit. Yeah. So this is how we can shape the line further. All that's left is now to finish the animation. We'll define something like a pulse that will drive the movement. The modulo function is a good fit for this, making use of both the time variable and the aspect value that I defined at the beginning. It will look like this. Okay, and let's put it right before mixing the colors. So right after the float line definition. Float pulse pos for the position is, as I said, modulo mod of aspect plus UVX minus time to make it animated and aspect. Okay, and we also need to subtract the aspect value. Okay, now we'll use this result for a new color blend. So the next line is float. Let's call it grid pulse, and it is going across this grid in the background. And again, the S macro, now with parameters negative 0.1, 0, and our pulse pos value. All right, we'll also modify our existing blend this one, so that in addition to line, it also takes grid pulse into account. And it's simple. So let's just multiply line with grid pulse. Okay, yeah, and something is going on right here. We have the first version of the pulse. But of course, the effect still feels like it's missing something. This is where we'll finally make use of the fall off function. So this grid pulse will be improved by multiplying by fall off with parameters pulse pos times 2. Okay, wait for it. And yeah, I think that already looks pretty good. The last detail I'll add is a highlight at the leading point. This one and this one. Highlight of the animation. I'll write a function called add highlight where I'll do everything that's needed, simulate the same periodic movement, follow the same curve, and blend a bright highlight into the final color. We'll calculate the periodic motion a little differently this time, because instead of darkening the part of the curve behind the current position, we'll want to illuminate the point at this exact current position. Okay, and once again, I expanded this window and write the function. It will be a little longer one, so I hope I won't make too many typos, but it's the last helper function we will need in this tutorial. So let's add it right after closes segment and right before the fragment function. Void add highlight, highlight with parameters in out, vec3 color, vec2 UV, float time, and float aspect. Okay, so as you probably remember from previous tutorials, in-out prefix means that we will change the value of this vector color inside the function, and the changed value will be used outside here in the fragment function, because we need to add the highlight into the final color accumulator, I would say. Okay, so now let's write the body of the function. Vec2 pos for position is vec2, and again we'll use the modulo, but as I said, a little bit differently. Time and aspect times 2 minus aspect and 0 for the y coordinates, because we need to calculate the y coordinate across the all the 13 points of our curve. And then for int I from 1, again iterating over the array, I less than points dot length, and I plus length and I plus plus. Okay, and now the body of this loop. Vec2a is points I minus 1. All right, and vec2b equals points I. Okay, this time I assign them to these helper variables because we will need these values at multiple places, and I don't want to copy and paste just points with indexes. All right, and now we need to do it only if the current position is within the range of the current segment. So if pos x is greater or equal to ax and pos x is less than bx, in this case, let's set the pos y, which is a mix of a y, b dot y, and pos x minus ax divided by bx minus ax. Okay, pay attention to the brackets. It's important that we use all of them at the correct positions. What exactly is not correct here? X, pos x, ax, bx, ax, a, b, unknown identifier in expression x, sorry, dot. Okay, very well. Now let's define the distance. So float dist equals distance function of uv and pos. By the way, you might have noticed that in other tutorials I use length of uv minus pos instead of distance uv pos, but both functions internally do the same, so it's just a matter of taste. All right, and now the color. So vec3, let's call it dot color, equals again a mix of, and we'll mix it with the white color because we want it to shine, and the line color, which is our green color, and the weight would be 0.5 times smooth step, okay, of 0, 1, and the weight is this time 3 times this, so we'll have a smooth transition between the shades of these colors. And finally, a float, let's call it line again, would be the fall off. Oh no, I think this time it's not a line, it's a dot, so let's call it alpha. That would be more appropriate. Is our fall off function we finally use uv.x divided by open bracket dot blur, another parameter, and plus 400 times this again the result of previous experiments to make it look as good as possible. All right, and finally we can modify the variable color, which is all this about. Color is increased by plus equals dot color times alpha. Okay, perfect. And let's add this call to the fragment function right after our last mix. And again, I'll show the 2D editor so we can immediately observe the result. So the mix is, I think, right here and here. Add highlight of color, UV, time, and aspect, and semicolon. Wait for it. Okay, something is here. This looks nice. But notice that the bright highlight only appears about half the time. That's because the effect consists of two identical halves, and we're only adding the highlight to one of them. So we can easily fix that by wrapping the entire calculation in a loop. Let's again show the whole window and find the add highlight function. And here, as I said, we will add the loop as the first line for, and let's call it, for example, float D, I think for distance or something like that, from 0 to D is less than 2, so it will have only 0 and 1 values, and D++. And now, open bracket, let's delete the closed bracket and find the end of the function and close the curly bracket, and we can fix the indentation. So this is a simple trick. Let's select all this line and press Tab key, and it is indented correctly. Okay, and now if we take a look at this again, okay, nothing is happening right now. Yes, of course, because I forgot the most important thing this time. We need to find this line, vec3. Again, in the add highlight function, vec2 pose is vec2 of dot time, mod time, and we need to subtract aspect and multiply it by the D value. All right, and now if we take a look, the dot should appear in both halves of the effect. Okay, and that's it. We are done. Now we can experiment in the inspector by adjusting the blur or sharpness of this highlighted dot. So let's find it. And dot blur increasing. Now it's very blurry, almost invisible. And going back to 0, now it's very sharp. Okay, let's get back to 1, which is, I would say, the best looking value. Thank you very much for watching. For a simple ECG display, perhaps one shown in the background of a hospital scene, the shader should be perfectly adequate. If we wanted to change the shape of the waveform based on what's happening in our game, we could simply replace the constant points array with an array parameter and pass the point coordinates from a script. That would let us easily switch from a normal heartbeat to a flat line, for example, or to any other waveform we might need. Anyway, take care, good luck with your Godot games, and I'll see you in the next video.